All right, good morning, everyone. Good to see you all back in the classroom. One thing I want to point out is this whole week we're going to be on advisement bell schedule. So if you, I think they sent it out in the email, but if you want to take a picture of that, we'll be on that bell schedule, because I think they want to try to run some drills over the course of this week, and they're just all going to do it all during our advisement time. So I think next week we'll be back on regular bell schedule, but we'll be advisement this week. Also, I'm going to have help sessions for during this week, Wednesday morning, Wednesday afternoon, and Friday morning. It'll be in the classroom, but also we'll make it available on Teams. So I'll send out a Teams link if you want to join, or you can also look on my website. After I record it, I will put those up. So if you're unable to attend them, you can still watch those recordings. Okay. So you guys picked up 2 packets. One packet was from 4.2. So we still have a couple of worksheets that we didn't get to. We'll either get to them this week or next week. Some of the works, the handouts are meant for test review. So we'll kind of pick and choose through those pages that we don't get to. And then also you picked up 4.1, which we started on Friday. We'll get through a lot of it today, but I think we're also going to spend a little bit of time tomorrow finishing up, and then we can start quiz review tomorrow, and then review Wednesday, review Thursday, and our quiz will be on Friday. Okay. Hopefully you guys have been keeping up with each of the homework assignments. The 4.6, I'm also going to check as well. We didn't get to it on Thursday, but we did cover trapezoids on Friday. I will send out a reminder this afternoon. I'll also send out a reminder tomorrow afternoon, and I'm going to be checking all the homework assignments on Wednesday at the beginning of class. Okay. Okay. Any questions about calendar for this week? Okay, so let's pick up where we left off with power rule. We talked about how power rule for integrals is really just the opposite procedure of power rule for derivatives. So a lot of things will feel similar. We still have a variable raised to an exponent, but now instead of multiplying and subtracting, we're going to be adding and dividing. So operations will feel a little different, but we still have kind of a 2-step process for power rule. Okay. Let's pick up where we left off on the second page. Power rule for integrals, we are still relying on the power rule conditions that we learned from first semester. So the conditions for derivatives and integrals are the same. Okay, we still need our variable. We still need to resolve any radicals, right? So radicals need to be converted to rational exponents. Variable can't be in the denominator. If it's in the denominator, we can't do power rule. Maybe we can apply other rules that we're going to learn later. But if you don't do power rule, the variable has to be sitting in the numerator spot. Okay. And then if we want to do power rule, all the parentheses have to be resolved, right? And if we can't resolve the parentheses, then that's for future problems that we'll have other rules for. But if we just want to do power rule, all three things has to be in place. Okay. I think we got through a couple of examples. Let me just review them. If I have integral of 7x dx, that term is set up and ready. No issues. All our conditions have been met. There's a hidden 1 as the exponent, so we just apply power rule. We take that exponent, we add 1 to the exponent, so 1 plus 1 is 2. Whatever shows up as your new exponent, you're just going to copy that number down below in the denominator. Okay, so these numbers will always match. Okay, 7x squared over 2 plus c. You can also push that 2 in front along with the 7 and make it 7 over 2 x squared plus c. I think visually, most students prefer it this way. It just doesn't, staring at that 2 in the denominator kind of feels a little messy. So I do encourage students to push the numbers out. It doesn't feel as intimidating not having to stare at the number below the variable. Okay. Notation-wise, as soon as you apply power rule, your integral and your dx notation will go away. In place of it, you're just going to have the resulting power rule term that you did, and then the plus c. Okay. So as soon as you apply power rule, your integral notation and your dx will go away. Okay. We also did a problem here where we had a constant, right? Integral of 7 will just become 7x plus c. This feels like an easy process, but I will say that it is also easy to make a mistake, because when we see this problem, when we see just a constant sitting there, our natural inclination is just to make it go to 0, right? Because we're so used to our derivative process. We have to understand that we're going the other direction now, right? So every degree is going to rise by 1. It's not going to fall by 1. So 7 doesn't go to 0. 7 will turn into 7x, right? Now, if we go backwards, this should make sense derivative-wise. We know 7x derivative is 7, so that step makes sense. Right? But integral, we're making our degree rise by 1. Okay, number 2, 7x cubed. Everything is set up and ready for power rule. So we get 7x to the 4th over 4. We can pick up the hand. 7x to the 4th over 4. You can also push that 4 out in front as 7 over 4, and then x squared plus c. Okay, number 3. Still no conditions that have to be resolved. Everything is set up and ready. No variable denominator, no radicals, no parentheses. So we jump directly into power rule here. 2x becomes 2x squared over 2. 3x squared becomes 3x cubed over 3. 5x to the 4th becomes 5x to the 5th over 5. You could argue that every term has its own plus c, so you could say plus 3c. But we know that 3 times c is still a constant, so there's no need to keep track of our individual c's. We just put it all together, make it all go into one expression, and make it just say plus c at the end. Okay, so there's no need to keep track of our c's, just say plus c, and that's enough. Okay, number 4, 3x minus 1 squared. This is a problem that we have to resolve condition-wise. Okay, radicals is not an issue. Denominator variable is not an issue. It's the parentheses that's the issue. Okay, we have to make sure we get that squared resolved, because we're not getting a clear view for what we can do with power rule. So we're going to FOIL this out. (3x minus 1 times 3x minus 1). We get 9x squared minus 3x minus 3x plus 1. Okay, everybody okay with expansion there? So no calculus yet, but we've gotten to the point where every term is ready for power rule. Okay, so 9x squared becomes 9x cubed over 3. We add 1 to the exponent. Whatever shows up in the exponent is going to show up below. 6x, there's a hidden exponent of 1. 6x becomes what? Over 2. And careful with that 1, what does that 1 turn into? Good, because it's x, right? You got to fight that natural tendency of making it 0. We got to make it plus x. It's not going to go to 0. We're not doing derivatives here. Okay. Do a little bit of cleanup. Okay, questions with 4. All right, number 5. We have x plus 1 over square root of x. Now we're going to have to deal with more conditions that have to be resolved. That couple things here, radical have to be resolved. The variable in the denominator is out of place. We're going to have to push it up to the top. Now, if you push this up to the top, you have to put parentheses around the x plus 1. And I find that when I presented it that way, a lot of students would forget to involve both terms with the square root of x. So I think maybe a cleaner way so that we're not having to hopefully can avoid those potential mistakes. If I see one term in the denominator, I'm always going to try to split up into individual fractions. And once I split up into individual fractions, I'm going to resolve each fraction like a separate problem and then get each term ready for power rule. So I'm going to work at it from that perspective. I'm going to get that square root of x as x to the 1/2, but along the way, I'm also going to start splitting up. Okay, you can only split up fractions if there's just one, if there's no plus or minus multiple terms in the denominator. Okay, if there's multiple terms in the denominator, we have to rely on other more complex rules that we haven't learned yet. But if there's only one term in the denominator, meaning that there's no sum or difference of multiple terms, we can just split up into individual fractions. Okay, so I'm rewriting that square root of x as x to the 1/2, and I'm also thinking of this as two separate fractions. Okay, we haven't cleaned everything up yet, but we have gotten it to the point where we can think of this as two separate problems. I can bring this x to the 1/2 as x to the negative 1/2. Add the exponents. You can think of it as 1 plus negative 1/2, or you can leave it in the denominator and just subtract the exponents here. 1 minus 1/2 is 1/2. The second term, we can bring that x up to the top to get it ready for power rule as well. So now we have both terms set up and ready for power rule. Now we can apply power rule. All right, power rule, we add 1 to the exponent. Adding 1 is the same thing as plus 2 over 2. Okay, so once we apply power rule, we know that these notations will go away, right? Add 1 to the exponents. Okay, good so far? So we basically are at the answer. We just want to try to do a little bit of cleanup. So what can I do with that 3/2? I can push it up to the top as what? Yeah, I can think of it as taking the reciprocal and flipping it, right? Because I want to move that denominator to the top. So I can think of this as 2/3 x to the 3/2. 1/2 flipped is just 2/1 or just 2. Yes, question.
How does that just get that? Yeah, like how does that?
Right, so there's a rule that we can apply which says that if I have a to the m over a to the n, that's the same thing as a to the m minus n. I can just subtract the exponents. Or if you want to do this a different way, you can think of this as x to the first power times x to the negative 1/2. All right, if I push that exponent up to the top, it becomes x to the negative 1/2. And once they're at the same level, I can add the two exponents. So 1 plus negative 1/2 will be 1/2.
They wouldn't be multiplied?
No, they wouldn't be multiplied. So here's the distinction. If I have x to the 2 times x to the third, I'm going to be adding the exponents. However, if I have an exponent directly next to each other, then you're going to multiply them. Okay, everybody good with 5? Okay, take a look at number 6. Couple of things we have to resolve. Variable in the denominator, we have to deal with that issue. Radical in the denominator, we got to deal with that issue. And then there's a third issue, is that we can't do power rule if there are multiple y's that are next to each other. This is kind of like a parentheses issue. We have to resolve this parentheses. We're going to merge the y's together. Okay, we can't do power rule for y and power rule for square root of y where they're being multiplied. Okay, we need that to be just a single variable. So let's work towards that issue. That's resolving that issue. So if I can think of it as y square root of y as y to the first power times y to the 1/2, what is my new exponent going to be if I were to merge those y's together? Yeah, 3/2. Okay, we're making progress. Radicals to rationals. We merge the y's together, but it's still out of place. We're going to push it up to the top. Once it's pushed up to the top, then we can think about power rule. So we have to get to this step before we can even do anything with calculus. Okay? If you try to do a power rule anytime before this, you're not going to end up with the right answer. Okay, so now we're ready for power rule. Add 1 to the exponent, which is the same thing as plus 2/2. As soon as you apply power rule, your notations will drop out, right? You're just left with 3y to the negative 1/2. Whatever you have showing in the exponent is going to show up in the denominator as well. Okay. We're going to resolve this negative 1/2, flip this up to the top as -2. Good. Yeah, we're going to merge those together, make it -6. And then as a final cleanup step, we're going to push that y back down to the denominator. Make our answer with no negative exponent. Any questions so far? Okay, number 7, let's look at number 7. Number 7 is probably as complex as a power rule problem can get. But I want to show you all the different moving parts so we can kind of see all the steps that could be involved with a more involved power rule problem. So number 7, we're going to see radicals that need to be resolved. We see parentheses that has to be resolved. We see denominator that has to be resolved. And also, we're going to have to deal with potentially adding or subtracting variables with different denominators. We got to find a common denominator as well. So there's a lot of things going on here. We'll take it one step at a time. Now, I'm only going to go through this a specific way, which means that there are other ways that you can still arrive at the final answer. You don't have to clean up exactly the same way as I'm doing. So, but I'm just going to kind of show you, just want to kind of let you guys know that so you don't feel like you have to follow that. If your step looks a little different from mine, it could still be algebraically correct and we should still arrive at the same answer. Okay, so I'm going to try to do a couple things at once here. I'm going to try to get these radicals to be rational exponents, and I'm also going to try to FOIL this out as well. So it's not going to clean everything up, but I'm just trying to save some writing here. So that root x, I'm going to rewrite as 3x to the 1/2. That cube root of x, I'm going to write as x to the 1/3. And the 1 minus x squared, okay, careful that we're FOILing this out correctly. If you want to, I think it's helpful if you just indicate that you are having to expand 2 sets of parentheses. And that's going to leave you with 1 minus 2x plus x squared. Yes, that's fine as well. You can rearrange the order, no issues there. The way that I'm going to do it is I'm going to distribute the 3x to the 1/2 through. Then I'm going to separate into individual fractions. Another way that you could do this is you can bring this x to the 1/3 up as x to the negative 1/3. Get that resolved and then distribute everything through. But I'm going to take care of the numerator first. Okay. Distribute the 3x to 1/2 through. Remember, you're adding exponents if you come across another variable. There's a hidden 1. 1 plus 1/2 is 3/2. 1/2 plus 2, that's the same thing as 1/2 plus 4/2, which is 5/2. All right, so I have 3 terms up top, 1 term in the denominator. I'm going to think of it as 3 separate fractions, and then I'll resolve each fraction individually. All right, so I know I have to bring the x up to the top. I know I have to subtract exponents, but looks like my denominator is not quite matching yet. So I'm just going to rewrite the problem, get my denominators of the exponents to match, so I can have an easier time subtracting them. So each of these denominators here, between 2 and 3, I need a denominator of 6, right? Same thing here. 6 is the denominator. 6 is the denominator. Okay, 1/2 is the same thing as 3/6. 1/3 is the same thing as 2/6. 3/2 is the same thing as 9/6. 5/2, same thing as 15 over 6. Yeah, over x to the 2/6. Okay. All right, so now we'll have an easier time bringing those denominators up by subtracting exponents. 6 minus 2/6 is 1/6. So now we should be ready for power rule. Okay, so see if you guys can finish off the problem here, right? So all of this work is just to get the algebraic step ready for power rule. Right? But until you reach this step, you can't do power rule. Okay, so now apply power rule, right? Add 1 to the exponent, divide it by that exponent, see if you can clean up each of the fractions. Yes. Oh, the 2/6. That's the same thing as 1/3. I just want to find a common denominator between the 1/2 and 1/3 so I can subtract those two fractions. You can do that. I just decided to subtract the exponents rather than moving it to the top.
Oh, so you didn't change it. You just like found all the common.
Yeah, I found all the common denominator, and then my next step, I just went ahead and I subtracted it to use this property here.
Oh.
But you could bring that x to the 1/3 up as x to the negative 2/6. Then you can do 3/6 plus negative 2/6, which will still give you 1/6. So if you wanted to take this step from here, if you wanted to do you'll still get the same result.
No, I mean like if you take the x to the 1/3 and then the x to the negative 1/3, and
Yeah.
then multiplied it by the 3x to the 1/2.
So if I have variables separating the exponents, I have to add or subtract it. I can only multiply if they're directly next to each other. So if you want to bring this up to the top, this will become 3x to the 1/2 times x to the negative 1/3. It's not going to be 1/2 times negative 1/3. We got to bring that x along with it.
So then what would that be?
So this would be 3x to the 3/6, x to the negative 2/6. Because in order for me to add the exponents, I gotta have common denominators. So I can't just do 1/2 minus 1/3.
Yeah.
Now you can apply power rule.
Oh, okay. So you can still do it that way as long as you make them common denominators.
Yeah.
Yeah.
Okay, so now ready to apply power rule. We add 6/6 to each of the exponents. We'll get 7/6 over 7/6. Second exponent becomes 13/6. Third exponent becomes 19/6. Okay, so here we're already sitting at the answer. We're just now trying to get it resolved to be a little bit cleaner. So we would force that denominator up as 6/7, force this 13/6 as 6/13, and 19/6 as 6/19. And then multiply with any coefficients that's sitting in front. Okay, so this is a foundational rule. We have other rules that we have to learn, but this is the one that you're going to use the most often, right? So we really want to be comfortable with all the things that we can come across with power rules. So any steps that doesn't quite make sense, let me know so I can clarify that for you. Okay, any questions? Okay, I'd like for us to practice 2 more of these problems before I move on to the next topic. If you guys can go to page 3, and I want you guys to try number 20, 21, and 22, bottom of the page. Just more fractional problems for us to kind of practice splitting up, getting it ready for power rule, and then applying power rule. So 21 and 22, bottom of the page, page 3. Does anybody still need this page? Okay. All right, try 21 and 22. Mm-hmm.
Oh, sorry.
That is
Okay, okay.
rewrite that radical. Split up into individual fractions. Yeah. Yeah, get ready for power. Okay, so this is what your cleanup effort should look like. As soon as you reach that last step that I that's showing, this is where we need to get to before we can apply power rule. Okay. Every term is set up and ready for power rule. Now we apply power rule. We add 1 to the exponent. Right? Whatever shows up as your new exponent, you're going to carry that number, copy it below the denominator, or copy below the division line. And then once you apply power rule, your integral notation, your dx notation drops out, plus c shows up, and then it's just a matter of trying to clean it up to make it a little more presentable. Okay, question with 21. Okay, try 22. Okay, what does x to the fourth over x to the fourth become? 1. Okay, no calculus yet, right? Still clean up. Second and third term also need to be resolved so that we can get them ready for power rule. Okay, every term is now ready for power rule. What does 1 become? X, yeah. Make sure we don't make it go to 0, right? That's the derivative process. We're doing the antiderivative, so 1 is going to become 1x.
When you bring it up, it's just x to the negative 4.
Say it again. Oh, that's right. When you bring the denominator up, because there's no numerator variable to worry about, it just comes up as 5x. It becomes x to the negative 4. And then every term, you just apply a power rule. You add 1 to the exponent. So negative 2 becomes negative 1. Negative 4 becomes negative 3. And if you have any leftover exponents in your answer, just bring them back down to the denominator. Okay, any questions, steps along the way here? Okay. The second part of 4.1 is trig integrals and differential equations. Go to page 7. Yeah, so in your final answer, I want positive exponents. So if you see any negative exponents in your answer, just resolve it by bringing it to the other side. Okay, page 7. So trig integrals, we're going to review trig derivatives. And really what I want to show you is that with the integral rules, we're really just working backwards from these trig derivative rules that we learned first semester. So really there's no need to memorize these new integral rules if we have these derivative rules in front of us. So if we can rememorize or review our derivative trig rules, that's all we need to help us get to these new rules. And we're going to see that with a lot of rules this semester, is we're really just working backwards from the derivative rules we learned from first semester. Now there are potentially some adjustments that we have to make, but for the most part, that's the big idea. We're just working backwards from the derivative rules from first semester. Okay, so let's review these first semester rules here. I like to have it in 2 columns with the C functions in alphabetical order. We know the C's will produce negative derivatives, so it's just a nice way of organizing our rules. Okay, so sine and cosine have similar looking rules. Tangent, cotangent have similar pattern. Secant, cosecant have similar pattern. Tangent and secant only involves each other, and then cotangent and cosecant's derivatives only involve each other. Okay, so sine of u becomes cosine of u times u prime. We know cosine's derivative is negative sine. And tangent just involves the one below it here, so tangent is just secant squared. And a secant just involves the one above it here, so secant is just secant tangent. All right, cotangent. Cotangent's derivative is going to have a similar pattern as the tangent. It's just, but it's going to involve the one below it. So cotangent is going to be negative cosecant squared u. Cosecant will just involve the one above it. Okay, all the C functions produces negative derivatives. Okay, so all this is review, right, from first semester. Now, we're just going to work backwards, okay? So if the derivative of sine is cosine, what do you think the antiderivative of cosine will be? Just sine, right? We're just really reading backwards, right? So the integral of cosine is sine, and that's what this rule tells us. Well, this is how we can arrive at this rule. Cosine just becomes sine, right? We're just working backwards, antiderivative. Don't worry about the u prime. Think of the u prime as du. Right, so integral of cosine u du just becomes sine of u plus c. Okay, now there are some adjustments we have to make here. We know the derivative of cosine is negative sine, so therefore the antiderivative of negative sine is a positive cosine. But what do you think the integral of sine must be then? Yeah, if we want to take the integral of negative sine, then it's perfectly fine to be cosine. But if I want to remove that negative away from the left side or from this side, it has to show up somewhere. So it has to show up in my antiderivative. It has to be negative cosine.
Does it give you reverse to all the ones with the series?
Not quite. But we just really have to look at the right side and convince ourselves what the rule is, right? Right, the integral of negative sine is cosine, so the integral of positive sine, I gotta move that negative somewhere. So I'm not having to memorize anything. I just have to kind of look at my rule and convince myself that I'm able to make the balancing necessary adjustments. So what about secant squared? Yeah, I find secant squared on the right side. Antiderivative will bring me up to tangent. I see cosecant squared show up here. I got to make a slight adjustment. All right. We know negative cosecant squared is cotangent. So therefore, positive cosecant squared must bring me up to what? Negative. Yeah, that negative has to be adjusted. So I got to bring that negative to be with that cotangent. Secant tangent, I see that expression on the right side. Antiderivative of secant tangent will bring me up to secant u. Okay, what about cosecant cotangent? Yeah, the negative has to go somewhere, so it's going to go with the cosecant. So if you look at the result here, it's not quite lining up as well as we want with the derivative rules. Derivative rules is nice, right? All the C functions produces negative, but not all the C integrals produce negative, right? This is kind of throwing us off a little bit. But again, you're just reading this off what you know to be true, right? You're not having to memorize this. Now, having said that, these do give students a lot of trouble just because we're so used to the derivative rules that the signs kind of throw us off a little bit. Right. The integral of sine is now going to be negative cosine. The integral of cosine is going to be a positive sine. And that feels opposite than what we were expecting from the derivatives. But it also makes sense because we're going the other direction. So things are going to be a little bit different because of that. Okay, so pay attention to these. These are the ones that it's easy to mess up on because of our familiarity with derivative rules and our natural tendency to just follow with what the signs that we're used to see. Okay, some of these classwork examples, it's just relying on properties, so I'm going to skip those. I just want to do a quick intro into differential equations and just want to show you that it's just another variation of taking integrals. It's the same power rule that we've done before. It's just the notations look a little different Just have to get used to those notations. So differential equations, it's just a fancy way of saying that I'm working with derivative. I'm working with an expression that's sitting at the derivative level. I'm basically just taking the antiderivative. That's basically what a differential equation is. I'm getting it ready for the antiderivative. Okay, so steps for differential equations. We're really just going to rewrite it in a different form. Rewrite y prime as dy dx. We know that these are the same things, it's just dy dx is a little bit more descriptive. We're going to separate the variables on either side of the equation. So we want the y's on the left, x's on the right. And then we're simply going to take the integral of both sides. Okay, so let's do an easy example here. Suppose y prime equals 2, solve for y. Okay, so y prime is really saying I'm basically f prime equals 2, but we want to just get practice writing it in a form that we're going to have to get used to. So think of y prime as same thing as dy dx. It just means that I'm finding the derivative. With respect to x, my derivative is 2. I want to find the antiderivative, but I want to separate the variables. So I want the y's on the left, x is on the right. I'll move that dx over to the right side. If it helps, we can put a 1 as it's really a coefficient of 1 in front of that dy. Okay, so now we're going to take the integral of both sides. Y's are separated from the x. We want the y's on the left, x's on the right. Okay, we're taking the antiderivative here. So left side is in terms of y. What do you think 1 dy is going to turn into? Just y, okay? Now, technically, there's a plus c. Let's talk about that in a moment. The right side, good. Dx tells us that x is the variable that we're working with on the right side. 2 doesn't go to 0. 2 becomes 2x. Now, we're looking at those plus c's, and we're saying, well, can't they just cancel out? But those c's could be different values. So all we need to do is, yes, technically it shows up on the left side, but we're just going to make it all show up in one location on the right side. So typical notation is we just have the plus c that shows up on the right, on the left, just merge it to the right, and we just have to make it show up one time on the right side. Y equals 2x plus c. Yeah, that's it. So you're just doing power rule. Just the notation feels a little bit strange. You want to get used to that. All right, see if you guys can continue with your homework. Keeping up with those, I'll send out a reminder. I'll be checking your homework on Wednesday. Thanks, everyone. Bye, have a good day. Bye, have a good day. See you. Have a good day. Bye, good day.